So now I'm going to illustrate for you the product rules for vector functions. And a nice way to use them is for finding conservation laws in physics. And this also makes sense because, like, if I give you a concrete formula for a vector as a function of time, then it doesn't make a lot of sense to try to use the differentiation rules, like the product rule and the others, for doing that. Rather, what we want to do is like work more abstractly. So, for example, suppose that as an example, let me give you the formula for the angular momentum of a particle, which is a cross product of the position with the linear momentum, which is just mass times velocity. So it looks something like this. And here m is a constant. So as I was saying, this is the formula for the angular momentum of a particle. And let's assume that the particle is moving in time. So the angular momentum may be a function of t. So really we want to think about it in this way. Mass is a constant, so the only two things that could be changing in this formula is the position vector of the particle and the velocity vector of the particle. But now we can use the product rules for the derivative of a vector to find the derivative with respect to time of this cross product. Now, as I was saying, the mass is constant, so if you want, you can take it out of the derivative. And then you just apply the product rule here. So remember that the product rule is like the same as the usual product rule for functions. You differentiate the first one and do nothing to the second, but now you just have to be careful about the order in which you write things and using a cross product instead of like an ordinary multiplication. But besides that, everything else goes through. And so what's the derivative of position with respect to time? You get velocity cross velocity plus r cross acceleration. Okay? And so remember the cross product of a vector with itself is a zero vector, so you can ignore this term, and so you just get m r cross a. But then you get r cross ma, and the reason why I'm rearranging it this way is that by Newton's second law, this is mass times acceleration is the force acting on a particle, so you get the net force, say, acting on a particle. So what we just found is that the time derivative of the angular momentum, and this is a completely general formula, right? Is this. Now, there are many forces in nature, like gravity. Imagine that now let's think of the particle as the planet Earth. And here you have the sun, which I think of as the origin of my coordinate system. So here's the position vector. Now, there are many forces in nature, like the gravitational force, that are centripetal forces, and that just means, let's call them a central force. If F is a central force, that just means that F is parallel to the position vector. So in that case, what that means, like for example, in the case of gravitational force, like the force would point towards the center of the coordinate system, or in this case, it would be between the sun and the Earth. And so remember that when you do the cross product of two parallel vectors, then their cross product vanishes because the angle between them is 0 or pi. So r cross f is 0 in this case. And so that tells you that dl, so what we care about is that this means that the derivative of the angular velocity is 0, and that means that L is conserved, right? Because this is the analog of the derivative. If the derivative of a function is 0, then that function had to be constant. So that means that L is a constant vector, or time-independent vector, and a time-independent quantity in physics is normally known as a conserved quantity. So usually you can find conservation laws in physics playing around with identities of this sort. And now, what does it mean to say that L is conserved? Well, remember that L, so the angular momentum is just, so here's R, P is just a multiple of the velocity. The velocity is tangent to the curve or to the orbit of the planet. So here's P. And so you have this vector L, which is the cross product of these two, but that's just, remember cross product is a perpendicular vector to the given ones. So that means that L is perpendicular. I should do it like this. L is perpendicular to these two vectors, but even if planet Earth is somewhere else, like here, another moment in time, right now you have a different position vector, but now you have different momentum. But since L is the same because it's conserved, right, that means that the motion has to take place on a plane. Well, it means two things. Like, for example, it means that if this radius shrinks in size, then the momentum has to increase in magnitude so that the cross product still has the same size in norm. Heuristically speaking, like the magnitude has to be conserved of the, right? So you cannot decrease R without changing the P somehow, or their angle. And so that tells you, like, that's somehow related to one of Kepler's law, that in equal times you sweep out same areas, because angular momentum, remember, cross product is related to the area of a parallelogram. So there's like some area conservation law here hidden as well. And also this tells you that the motion takes place on a plane whose normal vector is L, because L is not changing. So if you think of L, like, if say this is where the motion is taking place, so here's sun, here's Earth, L is still the same throughout the entire trajectory. So that means that the trajectory of the Earth is contained on a specific plane passing through the sun and the Earth. Okay, so notice that with very little knowledge, we have been able to draw a lot of interesting conclusions about this problem.